Welcome friends, Igor is here, and in this video we will cover elementary matrices. In this lesson we will define elementary matrices. We will observe that performing row operations is equivalent to multiplication by elementary matrices. We will also show that all elementary matrices are invertible, and we will prove that elementary matrices are in fact building blocks of all non-singular matrices. Let's get started. The motivation for defining elementary matrices is this. They realize elementary row operations through matrix multiplication. A square matrix is an elementary matrix if it can be obtained by performing one single elementary row operation on the identity matrix. There are three types of elementary row operations: swap, scale, and replacement, and therefore there are three types of elementary matrices. An elementary matrix Eij is a matrix that is obtained from the identity matrix by swapping rows I and j. Here is an example of an elementary matrix of size 3 by 3. To obtain this matrix, we swapped rows 1 and 2 of the identity matrix. An elementary matrix Ei alpha was obtained by multiplying row I of the identity matrix by a non-zero scalar alpha. Here is an example of such a matrix where we scaled row 2 of the identity matrix by 5. Finally, an elementary matrix Eij alpha was obtained by multiplying row I of the identity matrix by scalar alpha and adding the result to the row j of the identity matrix. Here's an example. This matrix was obtained by multiplying row 3 of the identity matrix by 2 and adding the result to row 1. Let me now illustrate that performing row operations on the matrix is the same as multiplying this matrix on the left-hand side by the corresponding elementary matrix. Suppose we swap rows 1 and 3 of the matrix A. Here we see the result of this elementary row operation. But you can obtain the same matrix if you take the original matrix A and multiply it on the left by an elementary matrix. And the elementary matrix was obtained by performing the same row operation on the identity matrix. Let's take the last matrix and scale the second row by 2. You can achieve the same result if you multiply the matrix on the left by an elementary matrix which was obtained when you scaled the second row of the identity matrix by the same scalar 2. Finally, let's perform a row replacement operation on the previous matrix. Let's say we multiply row 3 by 2 and we add the result to row 1. This same result can also be obtained if you multiply the matrix on the left by an elementary matrix which was obtained by performing this same row operation on the identity matrix. Let's record this observation for convenience of further reference as a theorem. It says that to perform one row operation on the matrix A is the same as to multiply this matrix on the left by the corresponding elementary matrix. Next, let's prove that elementary matrices are non-singular. We have established previously that a matrix is non-singular if and only if its reduced row echelon form is the identity matrix. And this is what we are going to use here. Let's say E is an elementary matrix, and we will prove that it is non-singular by showing that its reduced row echelon form is the identity matrix. There are three types of elementary matrices, so we will cover each type at a turn. If an elementary matrix was obtained from the identity matrix by swapping rows I and j, then to reduce this matrix back to the identity matrix, we again swap rows I and j. If the elementary matrix was obtained by multiplying row I of the identity matrix by non-zero scalar alpha, then to go back to the identity matrix, we scale row I of this matrix by 1 over alpha. Finally, if the elementary matrix was obtained by multiplying row I of the identity matrix by alpha and adding the result to row j, then to go back to the identity matrix, you multiply row I of the elementary matrix by negative alpha and add the result to row j. In essence, each elementary matrix was obtained by performing one single row operation on the identity matrix, and all row operations are reversible, so we can always go back to the identity matrix. We also know that for a square matrix to be non-singular is the same as to be invertible. In particular, what we just proved shows that every elementary matrix is an invertible matrix. In fact, we can derive the inverses of all elementary matrices from the proof of the last theorem. The inverse of a matrix obtained by swapping rows I and j of the identity matrix is the matrix itself. The inverse of an elementary matrix obtained by multiplying row I of the identity matrix by non-zero scalar alpha is an elementary matrix obtained by multiplying row I by 1 over alpha. And the inverse of an elementary matrix which was obtained from the identity by multiplying row I by alpha and adding the result to row j is the elementary matrix which is obtained from the identity matrix by multiplying row I by negative alpha and adding the result to row j. So this shows that not only are all elementary matrices are invertible, but also the inverse of each elementary matrix is again an elementary matrix. Moreover, it is an elementary matrix of the same type. And now, let's prove a remarkable fact that elementary matrices are the building blocks of all non-singular matrices. Namely, every non-singular matrix can be expressed as a product of elementary matrices. Suppose A is a non-singular matrix. We need to find a list of elementary matrices, let's say E1, E2 through Et, such that A is the product of these elementary matrices. We know that each non-singular matrices can be row reduced to the identity matrix. Because each row operation is reversible, this also means that there is a sequence of row operations that transforms the identity matrix into the matrix A. So we take this sequence of row operations that transforms I into A, and we write the corresponding elementary matrices. Then let's start with the identity matrix and apply the first row operation in the sequence of operations that transforms identity into the matrix A. We just established that performing this row operation is the same as multiplying on the left by the corresponding elementary matrix. Then we apply the second row operation in that sequence, which is the same as multiplying on the left by the corresponding elementary matrix. And we keep doing this. Every time we apply a row operation from our sequence, this is the same as multiplying by the corresponding elementary matrix. What will we get in the end? Well, this sequence of row operations transforms the identity matrix into the matrix A. But then, by the property of the identity matrix, it simply disappears from the product, and we have exactly what we wanted. We have expressed the matrix A as a product of elementary matrices. So, elementary matrices are small building blocks that can be used to produce all non-singular matrices. Think of an analogy with positive integers. Every positive integer greater than 1 can be expressed as a product of prime numbers. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will establish many interesting properties of the determinant, and we will discover why it is useful to know the determinant of a matrix. I will see you later.